is something that this session is being recorded. Yeah. So okay, I think we are on. Well, I think we can start this seminar. Well, welcome everybody, and thank you to join us in our seminar series of the Rock Glacier Inventories and Kinematic Action Group. Today I have the opportunity to present Jan from the University of Freiburg in Germany, not in Switzerland. The office of the Rock Glacier Inventories and Kinematic Groups in the Freiburg in Switzerland. So there's a Uni Freiburg in Germany as well, to be good. And he is going to present his work that has been developed in the Andes, in the Central Andes, especially in the Argentinian Andes, the Argentinian side of the Andes in rock glacier kinematics using optical feature tracking. So I think the room is for you. We have around 15 to 20 minutes of presentation, and after the presentation, we're open to questions. And also this presentation is being recorded as well. So just to let you know, all the floor is for you, Jan, and thank you for accepting the invitation.
Yeah, thank you, Sebastian, for inviting me and for having me, and for the very kind introduction. So in the next 15 to 20 minutes, I'm going to talk about deriving surface kinematics of Andean rock glaciers from feature tracking and optical imagery, even though I'm also presenting on some other aspects of my recent work. So as you probably are all familiar with rock glaciers and ice debris complexes, how I termed these glacier-connected rock glaciers, if you want. So I will not have to go into detail why we actually care and why we are investigating these permafrost features. But I'd like to quickly let you know why I think the Central Andes are a very amazing place to investigate cryospheric landforms, and that is why, and that is because in the Andes, in the Central Andes of Argentina and Chile as well, we find arid conditions, and these arid conditions favor the development of large rock glaciers and ice debris complexes. So when I refer to ice debris complexes, as I published a paper on this before the guidelines of the Rock Glacier Inventory Group were published, I'm referring to glacier-connected rock glaciers, yeah, some transitional landforms that develop a rock glacier type in the lower parts, but are connected to ice glaciers or even debris-covered glaciers in the upper parts. In the light of climate change, we are facing dwindling water resources. Yeah, so glaciers are diminishing, and that jeopardizes water security, especially in arid regions. And that is why I think looking at rock glacier and ice debris complexes in the Central Andes is very important. So the study I am presenting parts from today is based in the Cordon del Plata, which has a large variety of cryogenic forms. Besides glaciers and debris-covered glaciers, we have a lot of ice debris complexes and rock glaciers. The Cordon del Plata is quite close to Mendoza, so central Argentina in the Andes, roughly an area of 2,500 square kilometers, and its elevation rises up to 6 kilometers. So it has a quite extensive periglacial belt. So we find a large variability also vertically of these landforms. And in the beginning, the aim of my study was actually to investigate the regional distribution of surface velocities, or rock glacier kinematics, if you will. So we know some details on rock glacier kinematics in the Central Andes, or there were studies publishing on rock glacier kinematics in the Central Andes before, but our idea here was to actually provide a broader picture of a large assemblage of landforms. So when we investigate kinematics of rock glaciers and ice debris complexes, we have a certain set of methods. We can go there with RGIK, GNSS, do our surveys, we can do in situ monitoring, manual tracking, not tagging, in aerial imagery. All these methods have been available for quite some time, also using time-lapse photography. And the INSAR has been quite big in the last years, but also feature tracking automatically or semi-automatically in remote sensing imagery. And I thought I'll try this in this setting. So just to quickly explain what this feature tracking in optical imagery does and how it works, I will zoom into the Morenas Coloradas ice debris complex that is situated in the Cordon del Plata. Quite a large feature from the elevation between 3,500 and 4,500 meters, so quite some vertical extent as well. And what we did here, we surveyed with differential GNSS throughout the years 2017, 18, and 19, and also did some UAV flights. So we have some nice field data available, and I'm using this field data now to quickly show you what feature tracking in optical, or in this case, hillshade imagery would look like. So what you see here on the left-hand side is a flicking back and forth of two surveys we did on the lower part of this Morenas Coloradas complex in February 17 and also February 2018. Yeah, so you see that the central part, maybe I'll quickly highlight what I'm talking about. This central part here is moving back and forth in this flicking illustration here. So what feature tracking then does is we are selecting a point and a distribution of gray values, in this case from a hillshade, around this central point, and this is called patch. Yeah, we are looking at an image patch here, and then we are using a clever algorithm that is implemented in this EMT software published by Schwalbe et al. That uses a least squares matching approach to actually search the most likely spot of this gray value distribution in the subsequent image. And then if we kind of compare, I just drew some easy lines here for reference. If we compare two points in time, we can see that our rock glacier features, yeah, that's in this case, this furrow we are looking at here, we could call that a feature, has moved from one year to the other. Yeah, and so we can not only do this in hillshade imagery, but we can also go to other imagery. And in the paper, I just copied the head of this this paper here. In the paper, we were using rapid eye satellite imagery. Yeah, rapid eye satellite imagery, roughly a ground resolution of 5 meters. So compared to what you've seen before, quite a coarse resolution, but as most of the cryogenic features we are seeing in the Cordon del Plata are quite large and have some nice structured surface, it actually worked quite well to look at coarse resolution or high resolution imagery with 5 meter ground resolution. So we looked at in the northern part between 2010 and 2018, and in the southern part 18 was too cloudy, so we used the 2017 imagery. So we looked at two sets of images in these two parts, and we're actually able to successfully track 295 landforms within the Cordon del Plata range. 115 of these rock glaciers and 34 of these ice debris complexes showed an active displacement exceeding the level of detection. So our level of detection is quite high, so we cannot resolve, depending on the location, a bit, because image quality also plays a large role here. We cannot resolve displacements below, let's say, 20 to 40 centimeters, depending on the location. Yeah, so roughly 50% of the features that we were looking at in this study exceed this this threshold. Yeah, and what you see here is the 95th percentile of velocities of the tracked landforms, so rather a maximum velocity idea that we are getting here. And you see that we find a lot of features that move quite fast, at least exceeding 1 meter per year in this time span between 2010 and 2017 or 18. If we look at the entire distribution, or in this case, we are looking at the 10th, 50th, and 90th percentile of all these features that we were tracking successfully, we can see that the median velocities vary between 0.35. So for those with a lower threshold of or limit of detection, and roughly 1 meter ATIP per year. Yeah, and 1/3 of these landforms is actually moving faster than 1 meter per year. So quite fast features if we compare it to data from the European Alps, for example. But we also can see from the length of these arrows, you see in the figure here that we have a large variability between and within individual landforms. So that is why I thought we need to take a closer look at this. And these are just 4 illustrations where you see that within one landform, we see grossly varying surface speed. Yeah, and so my point would be, if we want to come to a very honest and complete representation of these velocity fields that are highly variable within one landform, we need to find a way to look at this in a bit more closer detail. And what we did is for that, we use flowline modeling, an approach published by Kienholz in 2014 for glaciers, but we adapted this for rock glaciers. And we created a rock glacier longitudinal profile, and then we created perpendicular segments along this, and try to use this as an illustration of how rock glacier surface velocity varies along the landform. And you see that for this specific Morenas coloradas example on the left-hand side here. And what I also plotted there is not only the velocity distributions within these rectangles perpendicular to the flow line, but also the mean slope. And you see that we find large variability, not just in the entire distributions, but also in the median values of surface speeds. And we kind of find a close association to the mean slope. So we can actually learn a lot from looking a bit more to the details of surface velocities. If we look at the temporal variability, I'm just showing you here 2 examples. So from Morenas coloradas, we are staying in this example. We have the rapid eye surface velocities I was just showing you before. And we can compare this to the UAV-derived velocities we were taking or deriving from our field surveys in 2017 and 18 in this case. And if we plot them against each other, or against, in this case, the ground measured RGIK GNSS values, we can see we find some very good agreement. So this is just to say that our method in this case seems to be working. So recent kinematics, as I termed it here, between 2010 and 2018, seem to be in quite a good agreement, despite not depending on the timing that we are looking at. And now I'm coming to some aspects of this work that I haven't published until now. In this case, we are looking at the past decades of kinematics. So there is some historical aerial imagery available from 1968. Sadly, the quality of this imagery is not high enough for automated tracking. So what I did is I did some manual tracking of large boulders or some features on the rock glacier surface or on the surface of this ice debris complex and compared it to our UAV-derived ortho image. And what we can see if we compare these two time scales with each other, so the velocity between 2010 and 2018 with the average velocity of 1968 to 2018, we see that in the lower ranges, we kind of get an indication of slightly increasing velocities, even though the higher velocities do not seem to show this picture. And if we compare this again to the velocities of 1 year, so 17-18 compared to 68 to 2018, we find an even better agreement. So in this case, I would argue we are not seeing strongly differing surface velocities if we look at the past decades in comparison to very modern, like recent surface velocity fields that we derive from our UAV surveys. And that is kind of in line with other studies from the Andes, but in sharp contrast to the findings that we know from the European Alps, where we can see an increase in surface velocities in the past decades. So this was my or our data from close to Mendoza, and then in the last year I was playing around with some data together with Daniel Velasky and Sebastian Vivero that come a bit more from the north. We are staying in Argentina, but we are moving roughly 1,000 kilometers to the north, to the Kachi range. And I'm just showing you one example here of what we did. This also unpublished work. This is one rock glacier. You might debate the exact outlines here. This is just taken from the Inventario, so the data that they provide. And we were looking at feature tracking in aerial imagery from 68 to 2009 ALOS data, and then the next time slice here is ALOS data from 2009 to CBERS data from 2020, and then in the last step up here, you see 2020 to 2022, so just the last 2 years, also based on CBERS data. And in general, the pattern of the upper two images you are seeing here is quite nice. So feature tracking seems to work. With the 68 aerial image, we still have some issues tracking the faster velocity parts. But still, we can kind of come up with a quick and dirty analysis of what our surface velocity patterns look like. And if we look at the distribution of this, we kind of get the impression that between 2009 and 2022, we don't really see any change in surface velocities, also in agreement with what I've shown you before. But we might see a slight increase in surface velocities from 68 to today, even though this might just be an artifact of the issues with tracking in the higher or faster flowing velocity regions within this landform. So what next? I'm just quickly showing you some stuff from the European Alps that we've been working on. I haven't had the pleasure to go to South America since the start of COVID, so rather focusing on some examples from a bit closer to here. And what we did here in this is the Kaiserberg rock glacier in the Austrian Alps. We also have some nice data that we can use for feature tracking on the rock glacier surface. And this rock glacier system consists of 2 units, Unit 1 in the north and Unit 2 more to the southeastern side. And these are showing grossly different velocity behavior. Yeah, you can see this Unit 2 is much faster than Unit 1. And we also can see that Unit 2 over the last 20 years, it's just 16 years, shows some signs of acceleration, while rock glacier unit 1, for that, the picture is not that clear. But interestingly, if we combine this interannual observations with seasonal observations, and this is work that Sebastian Buchelt from University of Würzburg has been doing recently, we see that on this slower moving feature, we see a clear seasonality with nearly no displacement during the early summer and the winter times, and then displacements pick up and rise in the summertime. And if we compare that to the same data set that Sebastian was computing for the second part of this rock glacier, we see there's much less seasonality in this faster moving part. And if we then have a look at subsurface information, in this case, we are looking at ERT data here, we also see that there is a distinct difference between the slower moving part that shows a nice seasonality with very high resistivities, rather indicating massive ice in the subsurface, to the second rock glacier unit with much lower resistivities and less seasonality in its moving pattern. So with this, I'd like to close my talk today. I guess I hope I could show you that Andean rock glaciers and ice debris complexes are interesting to look at. We found a high fraction of landforms that actually shows active deformation, and I think with looking into longitudinal profiles of surface displacement, we can kind of portray the entire portfolio of surface velocities quite nicely. And actually, we can use feature tracking in satellite imagery to update information on kinematics on a larger scale. And what I just wanted to show you with the last two examples from the European Alps, I guess it's very important that in the future we go to more rigorously combining our results from different methods, be it DINSA with feature tracking and optical imagery, or even other kinematic information with subsurface information. Thank you very much for your attention, and I'd like to also thank all the co-authors that have been working on the published and rather unpublished parts of this talk. Thank you very much.
Well, thank you very much, Jan, for the nice presentation about rock glaciers, not only in the Andes, but also here in Europe. And I think the room now is open to questions from the public. Please raise your hand or write something on the chat if you want to, if you have a question. Questions? Lynn, of course. Go, Lynn.
No.
You always ask questions, yeah, we know it.
Yeah, just one question about so in the final version of your inventory, which kind of other parameters do you document in the inventory in addition to the size and velocity? Do you have any other attributes you document for the inventory? And my question is a bit because we had some discussion last week with several people that are attending now regarding how to use kinematics or how to use velocity to give an information about the activity. So I was wondering if you use your velocity information to update or refine the activity assessment of the landforms. And if you did that, how did you deal with the fact that 50% of your landform are under the detection limit?
Yeah, a good question. I mean, in this case, so in the study in the Central Andes, I was using the outlines as contained in the Inventario Nacional de Argentina. Yeah, so I used a published inventory and just took the outlines and tried to track movement. And if I take my limit of detection at face value, if I just say, okay, everything I cannot detect doesn't move, then I come up with just half of the landforms that are actively moving. But then you are certainly right that we always run into this problem of what means rock glacier activity. Is rock glacier activity, so some significant movement? What is the threshold for this significant movement? If I, with my remote sensing analysis, cannot resolve movement below 20 centimeters, most of the rock glacier forms we see in the European Alps, at least large parts of these, would be considered inactive, or let's say in a transitional state, and that certainly isn't true. So my answer to your question would be, it's very difficult to actually include rigorous information on the activity based on remote sensing methods. At least if we do so, we have to find a way to make clear what the limitations of this surface displacement or of this activity state are. And yeah, limit of detection is one very crucial limitation of state of activity. Does that answer your question? Roughly.
Yeah, absolutely. I'm
okay.
mostly agree with you, because I'm more in the INSAR side, which has mostly the opposite problem, and I kind of like also your conclusion saying that we should work toward combining those, because we could overcome this problem of detection limit, partly at least.
Yeah, exactly. I mean, you certainly know the paper of Aldo Bertone and how they argue how to include kinematic information into rock glacier inventories, and I think it's a step towards the right direction, but we probably need to try to include the information from different methods, because one method alone always has its shortcomings. And if we combine optical data with field measurements with INSAR data, we can actually make a huge step forward, I would say. Yeah.
Yes, absolutely.
Good.
Thank you.
Do we have any other question? Jan, please go ahead. Jan?
Jan, hi, can you hear me?
We can.
Yeah, we
great.
hear you.
Yeah, great. So I've got two questions. First one is, I'm curious about the vertical changes of those large rock glaciers in your area, because those glacier connected and complex rock glaciers could undergo significant degradation at the same time. And also, to my knowledge, some rock glaciers in the Chilean Andes have been experiencing great magnitude of vertical thinning. So I'm wondering what's the situation for the rock glaciers in your study? That's the first question.
You want to pose the second question, or shall I first ask answer the first question?
You can answer the first question first.
Okay. So I have to confess that I did not analyze vertical changes in the entire study area, because I was just using optical satellite imagery. There's no information on vertical changes, so I didn't compute the EMs from the satellite imagery. What we have is what I'm showing you here. We can use our UAV-derived DEMs to actually subtract them from each other and say something on vertical or volumetric changes between 2017 and 19. What you see here is the lower part of this Morenas Coloradas ice debris complex or glacier-connected rock glacier. And it's quite interesting, and this echoes a bit what you were saying. If you look at the left-hand side here, we see this should be geographical unit 1, 2, and 3. 1 is the lowermost, yeah, the tongue, 2 is up here, and 3 is up here. So these are the parts that are more rock glacier-like and not debris-covered glacier-like, yeah, and these show some changes, but rather balanced changes, yeah. So we don't see a very negative behavior, and the changes are quite low. Whereas especially number 6 and number 5 here, these are the central parts where we find a lot of thermokarst features. So there is a massive ice below. So I would rather in this specific location call this a debris-covered glacier, protruding into the rock glacier feature at lower elevations. And here we see the dramatic negative changes. And that is kind of what you are also referring to. Yeah, so we see a lot of ice degradation, but this ice degradation is rather happening in those areas of the debris-covered glaciers. Yeah.
Thank you for your answer. Then I have another question regarding one slide where you showed an unpublished work about like you show the seasonality of rock glacier movement, and also you show some subsurface information detected by ERT. Yes, I suppose. I think this is very interesting because the two profiles have different seasonality and also different magnitude of surface velocity. So do you have like an interpretation for this?
So you mean exactly this? Are you still seeing the presentation? Yeah.
Yep.
Yeah. So
Yes.
this part where we find the higher seasonality in the part where we actually have indication from, I'd call this massive ice, or maybe the ice generation is just different. And this part where we don't see the seasonality and we have at least say a different subsurface composition. I'd be a bit cautious as to really say, okay, this information now means massive ice and this means just very few ice or something like that. Actually, as I put here, this is Sebastian Buchel's work. So he does his PhD in Würzburg University at the moment. And he sees a very similar pattern in different study regions. So he also assessed this in some rock glaciers in the Switzerland Alps. So there seems to be a robust pattern here, but I'm not too sure about the interpretation of this, because you also have to take into account that in this rock glacier unit 2, the slope is much steeper. So this is a steeper part of the rock glacier, and this is a less steep part, and that can also influence the seasonality of surface velocities. Yeah, I guess that would be
yes.
my very cautious answer to your question.
Yeah,
or
thank you.
maybe Sebastian has something to add if he's here. Oh no, I haven't seen him.
No.
Yeah. Okay. Thank you. I agree with you. There are many factors that could affect the movement of rock glaciers, including their likely seasonality behavior. But still, I think this is a very interesting finding. So thank you for sharing. I have no more questions.
Welcome.
Do we have any other question from the public? Any any other question. I might have a question myself for you. Just regarding the technique, are you using the EMT? And for me, it was not clear if you are using the hill shades of the optical imagery out of it, or are you combining both? And the second question, why you think the 68 images is very low, and then you end up doing feature tracking? Because what you showed, it was okay. I think the quality, instead of optically, I didn't see many issues like fingerprints or hair or things that goes into the. I've been working with storage all archive imagery, and sometimes you find drawings into the orthophoto. You don't have access to original scan films. You got so yeah. Those are my two technical questions.
Yeah, so the first technical question regarding what are you actually using for tracking? So during my work, I was comparing auto images as produced from UAV flights and hillshades as produced from UAV flights. And I got much better results with doing the tracking in the hillshades, because the hillshades kind of exaggerate slightly the surface morphology. And the problem with the autophotos was then that depending on the lighting conditions, you always run into problems that some features just have a different spatial spectral signature in two images. And then, yeah, at least for what I have been doing in Argentina and the European Alps, hillshade tracking was always performing better than tracking in autophotos. And then this autophoto from 68, I mean, you know that we already discussed that before. Even though the quality is quite good, just because here in the central parts we are missing a lot of information. So everything that is white was just not possible to track here. And that is because in this part of this rock glacier, of this particular rock glacier, the surface is so smooth that 50 years afterwards, we just don't find any matching feature on the rock glacier surface. And this is especially the problem with the Morenas Coloradas rock glacier, because it's moving so fast. Yeah, you saw that movement rates are some 2 to sometimes more than 2 meters per year. And 50 years afterwards, some features look so different that the algorithm is just not picking that up as a feature anymore, or a similar feature anymore. And that is why I ended up with this manual tracking. I mean, especially in those parts where you have thermocast, your surface changes completely, and then automated tracking is really difficult.
Yeah. Yeah, just a quick comment back to the hillshade versus orthophoto. I think yeah, it would be nice. Probably I haven't done it. I wanted to do it once, that just to compare both once you have in situ data and really figure out which one performs better. Maybe there might be case by case, but overall, I think some people either use one on the other because which one is available, or which one we think it performs better, as you say, keeping the same, exaggerating the landforms of the rock glacier.
Yeah.
But it will be depend of the velocity, the surface texture of the rock glacier, and many parameters that probably we haven't accounted for to really figure out which one performed better in case by case study. But yeah, I agree with you. Sometimes the hillshades perform better because the orthophotos, they have a small snow patches, and then when you have a snow patches, it doesn't work. Yeah, so a nice way to filter those things is using the hillshade, as you say, to exaggerate the
I can just quickly show you this complicated figure that master students of me was just compiling, and she compared tracking in automosaics that are published by the government of Tyrol in this case, and drone-derived information. And even though we are looking at very similar times in this, or time spans, it's a bit complicated, I know. But my point would be, even though we are looking at very similar time spans here, we see differences in tracking auto mosaics and drone-derived data. And so this, just to echo your point, we should look into this a bit more systematically and see if there's a pattern to this.
Yeah. Good. We have a question from Reynald.
Yeah.
Hi, Jan. That's nice you are on this slide. I just have a question about it, but the ones you presented during the just before, this is where the data you presented is coming from. So what is there was a timeline?
Which one now?
So for this rock glacier in Austria.
Okay. So
this one, yeah, stop.
Yeah.
Now,
so
as the time series you presented just before. So
the seasonal.
The seasonal one.
The seasonal.
Sorry for that.
Yeah, no worries. It's always difficult with online seminars. So this one here.
Yes.
This is Sentinel-1 INSAR data. So what Sebastian does is using Sentinel-1 A and B, but I heard B is now decommissioned or doesn't deliver data anymore. Exactly, and so he processes Sentinel SAR data.
Okay, and what is it represented? Is the line of sight displacement or something like that?
Exactly, this is line of sight displacement and combining both lines of sight, so both ascending and descending orbits.
Okay, yeah. that means that you can detect the vertical motion. Also,
yes.
So it could be another component to your motion also, which can be significant in summertime.
Let me see if, because Sebastian provided me with this. Oh no, so this is technically the same data you were just seeing on the other slide, even though for slightly different parts of this rock glacier. But this is just showing seasonality, a weird kind of way, showing that this has a large seasonality and this one has a lower seasonality. Sebastian also has the vertical component of this, and you're completely right. That is also an important contribution to the seasonality. Yeah, to the picture we are seeing here.
Okay.
Yeah.
I'm just wondering about that, but because that so on the experience we have from the Swiss Alps is that usually it's a bit the reverse. That means the seasonality in the horizontal movement is much larger, where the resistivity is a bit lower, so there is a bit less ice and more water, and is much less, and even the velocity itself is less when there is more ice. So where there is kind of massive ice, so it's interesting. But the vertical component, this is a reverse, and that's the question about separating both from INSAR data.
I like that, because that would have also been my first guess, that the pattern would be vice versa, and that it was why I was saying, okay, we have to be careful here, because in this special case, the faster moving rock glacier unit is also the much steeper unit, and so I'm not making the point it is the internal structure, but the internal structure certainly plays a role in this, and yeah, so we need to look into that more carefully, I guess.
Thank you very much, and for your presentation as well. Very nice.
Thank you.
Thank you. I think we don't have more questions, but I want just to thank you again, Jan, for your presentation, and the audience for the nice questions. And I think we can conclude the seminar for today, and just give you all an invitation. We are giving a special seminar next week, last one of the year, about the action group activities. So it will be, Wednesday at the same time, next Wednesday. And all of you are invited to take part in this seminar discussion that will provide the current development and future steps of the action group, and especially towards the EUCOP next year in Spain. So that is all from my side, and thank you again, you all, for this nice seminar.
Thank you very much for having me. Thanks for the nice discussion. And I hope I can join next Wednesday. Are you attending the EUCOP